Hey everybody, I hope you're all doing well. So kind of want to go over some chemistry content and also we'll get into a couple activities a little bit later on. So let's kind of go ahead and get started. So really just to begin with to understand chemistry and matter, we kind of understand and differentiate the two. So anything that studies matter and how it reacts and how it transforms, how it interacts with everything else, we call that chemistry. It's one of the other branches of physical science. We know physics is one, chemistry is the other. And matter we've already kind of talked about is knowing that it's anything that has mass and occupies space. So it's the stuff that makes up everything. So what makes up you, makes up me, houses that we live in, the planet that we live on, all of that is considered matter. So we use these in a lot of different ways. We're going to talk about some of these today, but for example, one of them is, how do we learn about the moon? The idea of what the moon is made out of is like, well, we can look at the things that make up the moon. We talked about the giant impact theory and astronomy a little bit. So that's just one of many, many, many different examples of how we're using chemistry and matter to study the world around us. So kind of first, before we start talking too much about different things, we kind of need to understand the different phases of matter. Now, we know there's more than three, but there's three common phases. In elementary school, I'm not going to, even middle school, really, I'm not going to worry too much about higher, more than just three, or ice condensates, or plasma, or different things like that. So for common phases of matter, we have just the three: solid, liquid, and gas. Now, it's important to know kind of what really the definitions of them are. A solid is basically anything that has a definite shape and a definite volume. A liquid is an indefinite shape, meaning that it takes the shape of its container, but there's a certain volume. Gas, however, indefinite shape, indefinite volume. So what that basically means is I can take a gas, I can compress it into a small container, still the same gas. I can change the shape of the container and I can change the size of the container. There's still going to be the gas in it. So, like we said, plasma is another one. Isobos, condensates. We're not going to get into other states of matter really beyond these three common ones in elementary school. So if you look at it from a molecular standpoint, solids are also where the molecules are held closely, and I use the term closely loosely, which we'll get into in a little bit. The molecules are closely together. They're kind of rigid in place. Liquids, on the other hand, they're still kind of close together, but they have the ability to move around over and across one another. Whereas a gas is a situation where the molecules are completely kind of independent from one another and they're moving it, and they're not attached to one another. So on a molecular standpoint, that's some of the differences between solids, liquids, and gases. So it's how well they stick together to determine their phases. As we add thermal energy to a substance, the molecules tend to move faster. So everything has a certain amount of energy into it, even solids. The molecules that make them up are vibrating, they're moving back and forth. Well, the more that those things vibrate, the more that those things move, the more energy that we're adding into it, the faster they're going to be going. And they're going to reach a point where the bonds that are holding them next to the other molecules, they either start weakening or they completely break. If they completely break and the molecule's moving so fast it's free to move around, it turns into a gas. Now, the temperatures and the amount of energy that needs to happen is different among all the different various molecules that are out there. Some can do that at very low temperatures, others need to have very high temperatures, and that really is what makes things, for example, at room temperature. The gases that we breathe in don't need as much energy to be in that gas state, as opposed to I'm sitting here in front of a desk, so the plastics, the wood, they are held in place as a solid. So now, talking about gas molecules and kind of talking about the room, they are very energetic. To kind of give you an idea is that these molecules move at a speed of about 500 meters per second. Now, that is around 1100 miles an hour. So you might be thinking, well, jeepers, that's pretty high, and that kind of can't be right. So according to that, if you think about it, so if you think back to the classrooms that we're in, if I'm in a STEM lab and I'm on one side of the STEM lab and I breathe some, Swiffer perfume or really bad cologne or something like that nature, you would think, well, if it moves at 1100 miles an hour, everyone should be able to smell it right away. Well, that's not entirely the case. There's something that we need to think about called diffusion. And so I'm going to run to the simulation here. So this is a FET simulation we're going to be using. And so on the left, I'm going to be putting in, let's say, a whole bunch of particles And on the right, let's just say that's my perfume spritz. So I'm going to put in more molecules on the left. This would represent the normal amount of air. So I remove the division. And if you notice, a lot of the particles are moving around, but what happens is that these particles are kind of bumping into one another. And they're not, even though they're moving in a straight line, if you look at this as an overall, all these red molecules are still kind of over here. They're slowly starting to make their way over. But this is what's happening when, like, spray a thing of perfume. It starts out over here, but there's so many other air molecules are bumping into each other constantly, back and forth, that it takes a while for these red molecules to start getting to the left-hand side. Now, I'm also going to go back and I'm going to do another simulation real quick. So here's another PhET simulation. What I'm going to do is I'm going to put in some particles here. So I'm putting in a whole bunch of particles, and you can see as I'm putting them in, the particles are starting to move around. Now, like as I was talking before about adding energy, watch what happens when I add thermal energy. See how the particles start moving faster and faster as they're starting to bump and bump and bump into one another? Well, that's what happens. I could start with a solid, add thermal energy, and the particles start moving faster and faster and faster. And then as that happens, sometimes these molecules get energetic enough to actually turn into a gas. Now, if you notice, not all of them are moving at the same speed. Overall, they're moving fairly quickly, but you can look and you can still see some of them that are not kind of moving all that fast, but it's just a matter, but overall, on average, they're moving kind of quickly. Okay, so like I said, we call this process diffusion, where as we're going from one thing to another, these gas molecules, even though are moving very rapidly, they're bumping into one another constantly. So when we're adding energy, we're talking about these different phase changes. So like, let's see here, for example, when I go from a solid to a liquid, that's called melting. So you might want to think about like, oh, well, what would it go from a liquid to a gas? Well, that's evaporation. Now, boiling is, might have thought of that one, is when it happens at the melting point. So at the boiling point. But the entire process, like if I put a glass out, we can call it evaporation. However, going back from a gas to a liquid, we call that condensation. If I'm going from a liquid to a solid, you might have said freezing, which is, okay, kind of what we're doing, but the technical term we can call it is crystallization. But we can also go strictly from a solid to a gas. And that one's some of you might know that it's called sublimation. But going directly from a gas to a solid, which is the reverse of that, we call that deposition. Now, in order to do that, we need to change the amount of energy. Now, heat, in a chemistry standpoint, is the amount of energy in the materials. However, in a physics standpoint, heat is the transfer of energy from one thing to another. So we think of it as thermal energy. So when I go to the left, from a gas to a liquid to a solid, am I giving off energy to be able to do that, or do I need to absorb energy? Well, I give off. I'm releasing thermal energy. In order to go, though, to the right, to a solid, to a liquid, to a gas, I need to add thermal energy, so heat is absorbed into it. So when we're talking about these phase changes, how quickly these phase changes happens depends upon the temperature. So evaporation usually occurs at the surface, but if we raise the temperature enough, we can raise it to the boiling point. And that's where we get actually the phase changes to start occur, not just at the surface, but also underneath the surface. So that's a characteristic, which we'll talk about properties in just a little bit, for boiling points. On the flip side, you also have what's called the freezing point. Now, you're not going to really need to know this for elementary school, but how much energy you need to add and to raise it by a temperature and how much goes up is based upon that material. So the amount of energy I need to raise copper, for example, or something of that nature, is what we call the specific heat capacity of that material. This is also why if you go to the beach, the water feels cooler and the beach feels, the sand feels a little bit warmer. It all deals with the specific heat capacity. So here's a question to think about. Your next door neighbor is convinced that the only way an object goes from a liquid to a gas is to raise the temperature until you reach the boiling point and boil it away. So what could you say to your neighbor to convince him or her otherwise? So think about it for a second. All right, so hopefully you had the ability to think about what you would do to talk it over with your neighbor and convince them. And so on your worksheet, kind of write up your answer for me. So that's going to be one of your questions there. So now that we're talking about the phases of matter, we kind of need to start delving into matter a little bit more and start looking at elements. Now, there are a huge amount of substances in the world around us. If you even just look around in your room, you probably have plastic. Well, there's different types of plastics. There's probably paper. There's probably wood. There's probably ink. There, blah, 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 blah. There's all these different types of substances in the world. Well, all of these substances really come from a few basic number of atoms. Think about it like the colors. Red, green, and blue make up all the different colors of the spectrum. You can think about it like alphabet and the words, where all of the words in our language that we can talk about, which there's tens of thousands, if not hundreds of thousands of words, come from a combination of 26 letters of the alphabet. Well, all the things that make up the world today come from a base number of these elements. There's 115 that we know of today. 90 occur naturally. Several others occur in the lab. And we arrange these in what's called the periodic table. So if a material is made up of one specific type of element, it's what we call an element. So I'm going to show you a couple different periodic tables. So let's bring up the first one. So here you've probably seen these before, and there's actually a lot of different ways to view periodic tables. So with this particular element, I can click on, let's say, magnesium. And it gives me some information about magnesium, pronunciation, appearance. So there's a lot of information here. Physical properties, chemical properties. So that's just one type of website here. Properties, orbitals, different things like that. You can look into things here. So let's look at, again, magnesium at 273 Kelvin. So at 0 Kelvin, which is kind of, freezing point, it's a solid. Okay, so if we go back to here, this is a second table. And again, you can go and find many different websites and many different chemistry periodic tables that are out there as well. You'll see again, so like, well, let me click on magnesium again. Again, just more information about magnesium, melting point, boiling point, how many electrons, density, and you can scroll through. And there's just a lot of information here. So again, you have access to this website or to this PowerPoint, which will be loaded up for you. So you'll notice that when you look at a periodic table, you have these symbols. So magnesium was Mg, usually comes from the name, magnesium, hydrogen, H, helium, He. Sometimes, however, they come from their Latin name. So lead, gold, silver. Now, one interesting story about lead, the symbol for lead is Pb. Now, the Latin term for lead is plumbum. Now, an interesting little story about that is when we first started to have, water being able to be inside, the pipes were made out of lead. We have them as PVC now. Now, so if there was an issue with your toilet or something that you couldn't fix, who would you call? And don't tell me Ghostbusters, though I know some of you probably thought that. My mind went there as well, but who would you call? Well, if you had an issue with, maybe the sinks or the water pipes or something like that, you would call a plumber. Well, initially, those pipes, they weren't made out of PVC, they were lead. And so the name that we give to a plumber comes from plumbum. Sometimes the elements are named out of people. Sometimes the elements are named out of places. So in this case, germanium was found in Germany. Curium, named after Marie, Curie. So this is going to be this first video. Answer some of the questions, and I'm going to make you another one in just a second.